Okay students, today we will start unit commitment. So what is unit commitment? In a thermal power station, it is not economical to run all the available units all the time. Why? Due to economic reason. So depending upon the demand on the station, we will select the units and then we will load optimally. So till now, in the previous lectures, we have studied optimal loading on units, optimal load dispatch problem. Suppose we are having some demand, certain demand say PD on the power station. So to meet this demand, suppose we are already have selected 2 units. The selected 2 units are to be loaded optimally so that the total generations from the 2 units will be equal to PD. Is not it? That we have seen. But from where these 2 units came? The power plant may have number of units. Suppose the power plant is having 10 units. So our 10 units are having 10 different characteristics, and you are having demand PD. Suppose PD is 10 megawatts, and units are having, each unit is having enough capacity. Suppose each unit is having 12 megawatt capacity, like that. So what you did till now, already selected units were given to you. These are 2 units, corresponding characteristic equations or curve you know. So you have to load these 2 units optimally. That part is over. But how these 2 units were selected among 10 units or all available number of units? So this task comes under unit commitment. The units, combination of units to be committed to meet a particular demand. Is not it? Suppose you are having 10 units. So various combinations of 2 units will be there. Unit number 1, 3, or unit number 3 or 9, and unit number 7, 10, like that. Lots of pair will be there. So for each pair, you will get one optimal load dispatch problem to meet this PD. And corresponding to all pairs, you will get different operating cost, optimal cost. So those each optimal cost depends on the selected pair of units. So finally, you will get minimum operating cost corresponding to one optimal selected units. So that comes under unit commitment. So unit commitment is nothing, selection of combination of units to be committed to fulfill a particular demand. That is unit commitment. But optimal unit commitment is selection of or optimal selection of combinations of various units to be committed to meet the demand on the station. Is it clear to you? So step number 1 will be optimal selection of combination of units. Once the combination of units are selected, so second step will be loading each unit optimally. That we have finished in optimal load dispatch problem. So step number 1 is optimal selection of combination of units. Is not it? So that is done looking a unit commitment table. So how a unit commitment table is prepared, we will discuss today. On what basis we are going to select the combination of units for various demands. So demand on the station may be starting from lower limit of the smallest unit to the sum of the capacities of all units. Suppose we have 2 units, and lower limit is 1 megawatt for each, and upper limit is 10 megawatt for each unit. So we can meet the demand starting from 1 megawatt till 20 megawatt. Each unit is capable of supplying 10 megawatt. So for a demand starting from 1 till 20, we are capable. But demand may vary. Demand is not fixed. Demand PD is not fixed. It varies. it varies with the time. At this time, certain value of demand will be there on the station. Next time, maybe that is peak hour, so demand will be peak, right? So starting from lower range to upper range, the demand may be any value. So for each demand, our task is, first task is to meet the demand at any cost. And not at any cost, we will try to minimize our cost. So we will plan to meet the demand, whatever the demand is there on the station, with minimum expenditure. So we are talking about thermal power plants. So our units will be thermal units. So as we have discussed that, it is not economical to run all the available units in the plant. So based on the, depending upon the requirement, we will operate the units. So first task will be to select optimally, the combination of units will be selected, and then once units are selected, so loading will be done optimally. So we have not to do these loadings manually. Already programs will be there, developed programs will be there, corresponding sensors will sense the demand and accordingly units will be selected. So we will prepare one unit commitment table. Why table? Because demand is not fixed, it varies. So one table having the variation of this PD from lower to upper, a wide range that can be supplied by the plant, because the capacity of plant is also fixed. Depending upon the available number of units and their capacities, we know that our capacity is starting from lower range to upper, lower limit to upper limit we can fulfill. So corresponding to each demand, one optimal combination of unit will be there. And corresponding to each combination of unit for a particular demand, only one combination of loading on each unit will be there, that is known as optimal loading on the units. Is it clear to you? Okay, so once objective is clear, so how to prepare unit commitment table? For that, generally dynamic programming is used. Are you aware of dynamic programming? Okay, so first I will try to explain. Let us represent this symbol capital F X. We will read it. This is minimum cost of generating X megawatt by N units. What you wrote? I am writing here. Okay. This is minimum cost of generating X megawatt by N units. Obviously, unit will be, what will be the unit of operating cost? Rupees per hour. Is not it? And let us represent this, a small f in, this is cost of generating X megawatt by nth unit. So what is difference between these two symbols? This is capital, this is a small, and here this is function of x, and x is nothing but the megawatt, x megawatt total power, and capital, if we have represented by capital F, it means minimum cost of generating this by n units. Suppose n is 5, so 5 units are operating and total generations from the 5 units are x, and the loading on the 5 units are corresponding to optimal loading. That's why we have used minimum cost of generating. Otherwise, various other combinations will also be possible to generate X megawatt from n number of units. Is not it? But this is corresponding to minimum operating cost. This optimal loading, right? What about this? So this is not optimal loading. At any loading X, nth unit. So we have selected 5 units, means fifth unit. So if fifth unit is generating this much, or if this is x, so use different, say y, some different variable. So if y megawatt is being generated by fifth unit, nth unit, suppose for 5 unit, fifth unit, so x minus y remaining megawatts will be generated by n minus 1 unit, means 4 minus 1 and 5 minus 1, 4 units. It's not it. So we will formulate one recursive relation like this. This can be written as this is minimum operating cost corresponding to x megawatt generation by n number of units. So this can be written as, let us formulate this. Y is variable here. These are not variable now. Once you have selected the optimal loading, so those optimal loadings are fixed on corresponding units. That's why we have used minimum. But this is variable. This is cost. So 1y will be obtained corresponding to which the cost of generation will be minimum. Okay, we will see details. So first write this. Fny, now you know what is Fny, plus if y is being generated by nth unit, so remaining will be generated by n minus 1 unit, means you will write here if remaining units will be n minus 1 and remaining generations will be, this is x, this is y, so this will be x minus y. Can we write this? Minimum cost of generating x megawatt by n units may be written as minimum, means minimize, we have to minimize, our objective is to minimize, this is variable, and Fny, you know what is Fny, cost of generating y megawatt by nth unit plus remaining megawatts, that is x minus y. So this is capital, it means the same what we have represented, minimum cost of generating x megawatt minus y by n minus 1 units. So how many number of units? N minus 1 plus n, and total generations x minus y plus y x, and we have used here minimum, so that will be obviously this. This says that minimum cost of generating x megawatt from n number of units. So we have formulated this recursive relation, and we will use this to prepare optimal unit commitment table. Clear? So before preparing unit commitment table, what should be known? You should know your units, number of units, and second point, their characteristics. Only number is not enough. You know how many numbers of units are available in your plant that can be operated depending upon the requirement. A second thing is, you should know the characteristics of each unit. Otherwise, how can you decide that which unit to be loaded optimally or like that, right? So you know your number of units and their cost characteristics. And what was third? Demand. So demand, basically demand is not fixed. So we will say demand cycle. Is not it? At what time, what is demand? Because demand is varying. So we will have a complete range of demand. Clear? So once you know these three informations, so you will start preparing unit commitment table. And second thing, we will assume certain fixed step of power to be increased on each unit. Suppose unit 7 is operating and you are going to increase the loading on that. So here we will assume that we have a fixed step. That step may be any. So here we will use a simple 1 megawatt. Suppose unit 7 is operating at 10 megawatt. So next, if you are going to increase the demand, then that next will be after 10, 11, then 12. If you want to decrease, then 9, 8 like that. So in a step of 1 megawatt, the variation or a fixed uniform step for each unit. For each unit, we will assume that the increment or decrement will be fixed And that here in calculation, in our calculation, we will assume that that is 1 megawatt. If you want, you can take half megawatt, that will be more accurate. If you want, then you can still reduce the steps, but it will require more calculation. So here we will calculate in classroom, but these calculations can be easily done with the help of program. No need to worry, right? Just try to understand the concept. Okay, so now we are ready to solve this recursive formula for preparation of unit commitment table. So we don't have available number of units. Let us assume in our plant we have how many number of units we should assume? Assume any number. If you assume 50, I don't have any problem, but you have to calculate for each unit. So let us assume just 3, 4, 5, right? Okay. 5, you want 5, okay. But calculation will be more. Let us assume 3 or 4, okay. Let us have 4, and if you wish, then I can give you home assignment for corresponding to 5, 6, or like that, depending upon your class real number, right? Okay, that is. So, unit number. First, we will try to understand the concept, how to prepare unit commitment table. Let us assume that we have 4 units in our power plant and corresponding cost characteristics. So you know that we represented our cost CI, cost of ith unit, is equal to obviously function of active power generation PGI. So we represented half AI PGI square plus BI PGI plus BI, because you see here, so we represented this. Why this fixed parameter? Okay, we can understand that although PG is not fixed, so with the variation of PG, cost will vary. But if even unit is not operating, PG is 0, even though we have some cost. Why? These are fixed costs. Suppose for 1 month power plant is not operating. Even though you have to pay the salaries of the employees, so by anyhow you should have some fixed parameter so that your other fixed expenditures will be recovered, because total expenditure is combination of fixed expenditure plus variable expenditure. So variable expenditure varies according to the generation, but fixed expenditure has to be recovered, is not it? Okay, so right here AI BI AI, this one BI and DI. What are these? You can write coefficients of operating cost characteristics. So these are coefficients AI, BI, DI. You are aware of that. So let us assume some values. So let us assume, okay, one more information is also required. Limits of the units. Is not it? Megawatt mean, megawatt max. So okay, we will include those also. So megawatt mean, just write here. You are aware of the symbol we used in very first lecture of optimal load dispatch. Megawatt mean, megawatt max, and these are unit number. So okay, 1, 2, 3, 4. Let us assume that lower limit of each unit is 1 megawatt. Right here 1, 1, 1. Means for first unit lower limit is, so below 1 megawatt you can't load. Is not it? Once that unit will be operated, once operating, it means minimum 1 megawatt loading will be there. Below this, either it is not technically feasible or not optimal, right? And let us assume some maximum values. Okay, let us assume it as 30. Let us assume at okay, 11, let us 12, let us have 50, whatever. Each unit will have its own capacity, lower and upper, lower limit and upper limit. So we have assumed some random values and assume some, okay, 1.0, let us assume 1.5, 2.0, and let us say 2.5, so that calculation will be easy. You can put any value. Let us assume this as 24, 26 or 29, 31 like that. And let us assume this as, okay, 8, let us assume 3, 5, 4, any random value. So for these given values of parameters and corresponding limits of the 4 units, we are going to prepare unit commitment table for a particular demand. So for each demand, one optimal combination of unit will be selected, and that combination may be for other demand also, is not it? Once these combinations are selected, then second task will be to load the units optimally, is not it? Are you getting? So let us assume some demand on the station. So first tell me the range of demand that can be met by the operating various units. So minimum range will be 1, because each unit is having 1 as lower limit capacity. Suppose, so how to get 1, all are 1? So we will see the lower limit of a smallest unit. So starting from that, what is upper capacity? So okay, 13, 11, 24 plus this, whatever coming out to be. So these are the complete range. What is coming out to be? 1 megawatt to 51. Okay, for this set of data. So PD may vary starting from 1 to 51. So let us assume our PD is at any point of time 8 megawatt. So what is our objective? You have to generate 8 megawatt. First thing, once you know that your demand is 8 megawatt, it means you have to generate 8 megawatt. So 8 megawatt can be generated by running this unit alone, this unit alone, this unit alone, this unit alone, or combination of any 2 units, this plus this, or this plus this, or this plus this, or combination of any 3 units, or running all 4 units. So how to decide how many units to be operated? So that is unit commitment. First thing is to select the combination of units to meet this demand. Okay, just observing the parameters of the units, you can say that this one is looking more efficient, is not it? Minimum AI and BI. Minimum, then so this is 1, AI is 1 here. So for C1 you will write half 1 into PG1 square, right? Plus B1 is 24, PG1 plus B1 is 8. Is not it? But this coefficient is more than this. This coefficient is more than this. So if you are asked to select any one unit, then you can guess, okay, we can select this unit. But it will not give the optimal operation always for each loading. You have to calculate. We will see, right? Okay, if PD is varying, so corresponding to that, again you will select optimal combination. Is it clear to you? So what we will do? We will solve this. So how to solve this? So first we will solve if 8 megawatt is loaded, given this load is given to the unit 1 alone. Then we will check if any combination. Okay, we will start. So first we will solve this demand. If here X is demand, we have to generate X megawatt, and that X is 8 megawatt here. So we will write here And first we'll check if all the demand is being met by unit 1 only. So this can be written as F18. How? What is capital F18 and what is small f18? This is minimum cost of generating 8 megawatt by 1 unit. And this is cost of generating 8 megawatt by first unit, right? Is not it? So it means if unit is 1 only, so whatever the cost is coming out to be, that is the minimum cost of generating that much megawatt. If units will be more than 1, then we can select. If 2 units are operating to meet 8 megawatt, it means lots of combinations will be there. Unit 1 may be loaded at 2 megawatt, this 6 megawatt, this may be 3 megawatt, this 5 megawatt, like that. But if unit is 1 only, it means a small f and capital F will be same, is not it? It's clear to you? And this is F18 is nothing but, this is better to write Fi. We have represented this Fi, cost of generating 8 megawatt, is not it? By ith unit. What is this? So instead of Ci, here we will represent Fi. Fi is same as Ci. So what is the value of this? So we have Fi as this. So it will be half A1 Pg1 square plus B1 Pg1 plus B1. Put the values. So A1 is 1. Okay. So half. And Pg1 is 8 into 1 into 8 square plus B1 is 24 into Pg1 is 8 plus D1 is 8. Take the values. 230 point. Okay.
Only 232.
Okay, rupees, whatever it is coming out to be, rupees per hour. It means now you have the operating cost as 232 rupees per hour. When the demand 8 megawatt is met by the unit 1 alone. This information you have. Now next task will be to check if this 8 megawatt is being met by combination of any 2 units. So select any 2 units. For ease of calculation, I have arranged in ascending order, but later we will observe that ordering doesn't matter. You can order your units randomly, and by using this method, no need to worry about ordering, no need to find out the efficiency of each unit, because efficiency alone is not enough. Some other parameters are also having some important significance, like efficiency. Apart from efficiency, what it will be? Reliability. If your unit is more reliable, although less efficient, so sometimes you will prefer that unit because of reliability. So some other factors are also associated. So no need to worry regarding ordering, just randomly name the units. Suppose you are having 100 units, start from any unit 1, 2, 3 up to 100. But whatever numbering once you have done, just mark those units and corresponding the parameters of the characteristics. Once it is available, so you will use this recursive formula and we will prepare unit commitment table. So till then what we have done till now, we have evaluated the operating cost if the demand is met by the unit 1 alone. That unit 1 may be any unit depending upon the numbering. Once numbering is done, so okay, start with that. So next task will be to check the operating cost if the same demand is being met by 2 units. But till now we don't know the optimal combination of units. So that's why we will check each combination. So first combination, let us say first and second. The first and second, so the representation of that case will be, now the number of units will be 2 and demand will be same 8. So this can be written as, you know this formula, will be mean y, this will be mean y, and this will be, what is n? 2 here, F2y plus F1 n minus 1, and what it will be? 8 minus y. Let's check it. Isn't it? What is our next step? We are going to calculate the operating cost corresponding to this demand 8 megawatt when 2 units are operating. It clear to you? Remember that each unit is having its minimum limit as 1 megawatt. So if somewhere 0 is coming out to be, it means units are not operating. Unit is not operating. Unless it is 1 or 2, 3 or like that. Because we have selected our step as 1 megawatt. So minimum loading will be 1 or 2, 3 like that. Is not it? Once loading is coming out to be lesser than 1 or 0, it means unit is not operating. Clear? Okay. So from this formula, we can write F28. You know what is F28? Minimum cost of, you are going to evaluate. What you are going to evaluate? Yes? Minimum cost. Your target is minimum cost. If that cost is lesser than this, then you will accept. If minimum cost evaluated when 2 units are operating is more than this, so no need to select 2 units. For this demand, 1 unit will be enough. That will be optimal, is not it? So your next step is to evaluate minimum cost of operating this demand 8 megawatt by 2 units. So this is variable y. What is this? Generating y megawatt from second unit, and remaining will be 8 minus y. And what is this? Minimum cost of generating 8 minus y by. So what will be the value of y? We have selected a step of 1. So y will be 1 megawatt. Then 2 megawatt. So once y is 1, so this will be 7. Okay, we will write it. Have you noted down this? Yes. Okay. So this can further be written as min, and y will be starting from 1 to, we will see depending upon the demand. So we will write F2 1, minimum loading will be 1, plus remaining will be F1 7. Fine. One combination is this. What is second combination? Write all combinations. Second combination is generating 2 megawatt from second unit, and remaining, this will be 6. This is also one combination, generating 8 megawatt by 2 units, in which this is minimum cost of generating 6 megawatt by 1 unit, first unit. So write all combinations. I am writing here. So next will be still F2 3 plus F1 5, and next will be F2 4 plus F1 4, F2 5, F1 3, F2 6 plus F1 2, then F2 7, F1 1. This is capital. Is it clear to you? So minimum generation is 1 only. Otherwise 6 to 8, 7 plus 1 8 is not it. Otherwise we can move further also, right? If your step is 5.5, so accordingly we can prepare the various combinations. Any doubt in this? Just we have written the same for this demand 8 megawatt. Similar procedure can be adopted for other demand also, right? So till now we have evaluated F1 8. We have not evaluated F1 7. That is required. So just evaluate F17. So as F18, minimum cost of generating 8 megawatt by first unit is same as generating 8 megawatt by first unit. So similarly, we can evaluate F17. That is nothing but F17. So evaluate it. Tell me the values. So this will be minimum of, and what about this? This is F21. What is F21? What is F18? Generating 8 megawatt by first unit. So this will be generating 1 megawatt by. So evaluate this also. So this side people will evaluate this one, a smaller one, and this side students will evaluate the capital one. So take me the values quickly. F21 is nothing but, see, this AI is 1.5, BI is 26, and DI is 3. So you have one relation for Fi, that is Ci, is equal to half PGI square plus BI PGI plus DI. This. So put these values. So this F21, 29.75. Okay. So this is whatever it is coming out to, just write here. Plus, tell me this value. 200.5. Okay. Okay, next one. F22, generating 2 megawatt from second unit. We have cost characteristic. So evaluate corresponding to this loading. 58.0. Okay, fine. Plus, what is F16? 170. 170.0. Okay, write it 170. Okay, 58 plus 170. Okay, next. 83, F23, right? 87.7. 75 plus F15, 140.5. Okay, what about F24? 119. 2. Okay, majority of you have evaluated as 112. F14. This is F14. Okay, 112. What about this? 119 was okay. Okay, next F25, generating 5 megawatt from second unit. 151.75. This one F13. 84.5. Okay. Next one F26, generating 6 megawatt from second unit. 186.0. Okay. What about F12? 58. Okay, next. 221.75. 32.5. 32.5. Okay, so finally we will write is equal to, so find these sums. This plus this is equal to whatever it is coming out to be, just write here. Next. Okay, just tell me quickly. Minimum I am writing here. This plus this. 230.25. Okay. Comma. What is this? 228. 228. What is this? 8.25. More than this. Okay. So we have this. Next, just tell me. 231. Okay. Next. 236. 0.25. 224. 44. Okay. Speak louder.
254.25.
Here, right? 254.25. Okay, all covered. 1, 2, 3, 4, 5, 6, 7. Okay. Okay. So now next will be minimum of these 7. So that is, which one is minimum? 230. Okay, 228. Okay, 228 is the minimum one. 228 rupees per hour. And what was this? 232. Focus here. F18 is more than F28. What does it mean? To meet this 8 megawatt demand, if you are operating unit 1 alone, which looks to be more efficient, just observing the parameters of the characteristics, if you decide, because the upper limit is 13, so first anyone can guess, okay, select the highest efficient unit, because our demand is 8 megawatt, that can be met by this unit, as the capacity is up to 13 megawatt, and more efficiency, this one is more 50% more than this. This is also more than this. Okay. So mainly these two parameters are affecting in cost. These are fixed. This is not it. But after these steps, we can observe that generating 8 megawatt, not generating, minimum cost of generating 8 megawatt by first unit is 232 rupees per hour, which is more than the minimum cost of generating the same demand 8 megawatt by 2 units, unit 1 and 2. So these combinations are optimal. And again, find out the combinations also. So this comes out to be corresponding to second, index is second one, and corresponding to second one, we have this. We got this value minimum among all combinations, and this is corresponding to this. So we will write this as, okay, we can write this will be equal to here F2 2 plus F1 C. Is not it? This is minimum cost of generating 8 megawatt by 2 units, unit number 1 and 2. Whichever pair you have selected, for that combination only we are talking about. Clear? So that is corresponding to the 2 megawatt loading on second unit and 6 megawatt on first unit. Clear? Task is not completed yet. We have just checked one combination. We have to check other combinations also. So what will be our next step? As of now, we have observed that generating 8 megawatt alone from first unit is not economical. Generating the same 8 megawatt from 2 units are more economical than this. So we will search if generating 8 megawatt by 3 units, by 4 units, available number of units. We can check various combinations. That might be possible. Depending upon the various values of the characteristic constraints. That is also possible. And no need to worry, unit commitment table is prepared once only. You have to prepare once only for a plant, for various type of units available in the plant, corresponding cost characteristics. Unless you are going to change in units. Suppose 2 units are replaced by 2 new units. So in that case, you need to prepare the updated unit commitment table. Fine. So what is next task? So our next, just note down this. Have you noted down? So this is just write the values. That is coming out to be 228 rupees per hour. Okay. So our next task will be, I am writing here itself. I am replacing, have you noted down, right? So I am replacing itself. And we will write, what we will write? 3. It means minimum cost of generating the same demand, that is 8 megawatt by 3 units. So our additional unit will be third one. First, second and third. So for that, we will write F3y, and what we will write? F2. Why? No need to check again for various combination of 2 units. Once you have got minimum cost of generating 8 megawatt by 2 units, so all other combinations are covered here because this is minimum one. Once 2 units are selected, and once you have obtained the minimum cost corresponding to a particular demand, so other combinations are also covered here. So that's why you will write 2 8 minus y. Clear? And y varies in the step of 1 megawatt as we have assumed in the beginning of the class. Right. So various combinations here will be generating 1 megawatt from, clear, and remaining will be, so here it will be, okay, so mark here 3, here 2, mark here 3, here 2, 3, here 2, everywhere 3, 2, 3, 2, 3, 2. So till now we have F2 8. We don't have F2 7. Using similar procedure, we will evaluate F2 7. You know how to evaluate F2 8. You know, right? So using similar procedure, we can evaluate F2 7. We can evaluate F2 6, and so on. Is not it? So corresponding values will be updated here. Is not it? And finally, lots of calculations are required here. So try to understand the concept only. Procedure, you are aware of the procedure now. You know how to evaluate F2 8 as we did in the previous step. So using similar procedure, you will evaluate F2 7, F2 6 like that. Right? So finally you will get one cost. So that cost will be compared with these two costs. So no need to compare with the previous one, as already we got here corresponding to F2 8. What was that? Just write here. F2 8 was 228 rupees per hour. Is not it? This is corresponding to F1 8 and this is F2 8. As this is lower than this, so you will compare this characteristic cost with this. Is not it? And you will take the minimum one. If this is further coming out to be minimum of this, it means the 3 units are operating 3 units to meet that 8 megawatt demand is more optimal than selecting 2 and 1. If this is minimum, it means this will not be optimal. Unnecessarily you are running one additional unit. So what will be your next task? Again you will check with the combination of 4 using similar procedure. Is it clear to you? And you will compare. So finally you will get, okay, we will prepare here instead. This is clear to you. So we will prepare units. Okay, first write here load. Load in megawatt, right here. In megawatt, load on the plant, and units, unit number. Okay, units to be committed. So units are unit number 1, 2, 3, 4. We have 4 units. So write all the numbers of units. So these are unit numbers 1, 2, 3, 4. Units to be committed. And load may vary starting from 1 megawatt. The next step will be, we have assumed our step as 2. So use that step as of now. So 2 and so on. We calculated for 8. So in between somewhere 8 will come. Right? Then 9 and up to, what were the 51. So up to 51. We will have such type of loads at any point of time. So suppose F38 is coming out to be more than this. Suppose, we don't know, we will calculate because randomly I selected some value and according to that we calculated. So unless the F38 is calculated, we can't conclude. But suppose this F38 is coming out to be more than this. So what will you conclude? And again, F48 is coming out to be more than this. So you can conclude that F28 is more economical. So to meet 8 megawatt demand, the units to be committed will be first and second. So we will write here this, cross here, cross here. Are you getting this? Similarly, you will calculate for 8 and so on, starting from 1 till all possible demands on the station, and you will mark here. So as of now, just put blank, and so on. So once unit commitment table will be prepared, you will get all positions filled. Clear? So just looking demand, you can decide the optimal combinations of units to be committed. Is it clear till here? You know what is this? This is optimal unit commitment table. How is it prepared? You know, we discussed just now. So once UC table is prepared, once only for a particular plant, you know the range of load that can be met by that power station. So at any moment of time, just sense the demand at that moment of time and compare with this, and corresponding units will be selected. Is not it? This is step number 1. What will be step number 2? Once a particular combination of units is selected, you will load each unit optimally to meet that demand. That we covered in optimal load dispatch. Are you getting? So finally, we will have one table I am having here itself. So it is not necessary that for each demand you will have different combination of units. Maybe for 8 you are getting 1 and 2. Maybe for 9 also you will get 1 and 2. For 10 you will get 1 and 2. Somewhere you will get one load where some other unit will come into the picture. Not necessarily 3 or 4. These data will be randomly because you have numbered your units randomly. So any number of units may be into the picture for a particular demand, right? So we will make it like this. Suppose 1 to certain demand A. We don't know as of now with what is the value of A unless all the loads are checked. We have just checked for 8 megawatt. This was 1 point corresponding to 1 to up to 51. How many points? 51. So out of 51 you have checked 1 only. Partially we have checked. So we will check while preparing unit commitment table. We will complete the table. So once table is completed, we will come to know the value of A. So whatever the value of A is there, A, the next will be A plus 1 to say B. Next will be B plus 1 to say C, and so on. So later on you will get here 51. Is not it? Is not it? Okay, let us say we are getting 5 combinations of such. So B plus C or C plus 1 to D and D plus 1 to say 51. As of now, just we know that this value 1 and last one will be 51. So suppose these were units 1, 2, 3, 4. So we can mark, like say somewhere you mark this operating, this operating, this not operating, this not operating. Similar signs will be similar. one can be done for other places. So this is unit commitment table. Now next, for each, as of now we have selected our step as 1 megawatt. So that will not be more accurate. If you are going to select 1 kilowatt, depending upon the nature of your unit, the step by which you can change the load on a particular unit, right? So if a step will be less, accuracy will be more. If a step will be more, accuracy will be less, right? So once this is prepared, for each load starting from 1 to 51, let us draw here. So starting from, say this is 1 megawatt, this is load P in megawatt, and up to this will be 51 megawatt. The plant operating cost characteristics will be evaluated. We have discussed the operating characteristics of each unit, unit 1, unit 2, various units, right? So finally you will have one such characteristics for the plant. That will be known as operating cost characteristics of the power plant. Are you getting this? So how these will be calculated? For each load, suppose 1 megawatt, you know which combination of units or which unit to be committed. For that unit, for that load, you will get cost. Similarly, for suppose any load in between this, you know the combination of units to be committed, and once combination is known, optimal loading you can calculate, and corresponding to those loadings, corresponding cost of each unit will be evaluated. Summation of all cost will be plant cost, so that cost will be obtained. So you will get one cost characteristics of the plant. Is it clear to you? Is it clear to you? Not clear? Clear. Okay. Any question till now? This was all about how to prepare unit commitment table. Obviously, optimal unit commitment. Any question? Are you getting or not? Yes. Clear to you? Thank you.